I just wanted to talk about quiz 2 a little bit. If there are specific questions, I can answer them. I can also just kind of quickly go over the answers, if that would be helpful. And I see from some nods in the room that it would be people would like to kind of see what the answers are. So I will do that quickly. So the first question was having a process having 2 pointers to the same process control block in the ready queue. What would the effect of that be? So any thoughts on what the effect of that would be? I think that people did pretty well on this question. So the effect would be, if you're in the ready list twice, it means every time you're at the head of the ready queue, you get to run. So it means you get to run twice as long as other processes. So if you're in there 3 times, you get to run 3 times as long. So another question is, how could you do the same thing with the round-robin policy without having multiple pointers? So some obvious options are, 1, you could just tell the scheduler when you run this process, have a little value that says what the time slice should be and just let it run for 2 or 3 times as long. Another option would be is when it's done running, instead of putting it at the end of the list, you can put it in the middle of the list somewhere so it gets to run again sooner. Any questions on that? Okay, so the second question was a 16-bit address with 64-bit pages. How many bits are in the offset of the virtual address? So you have 16 total bits. We have 64-byte pages. That means the offset is 64 bytes is 2 to the 6, so the offset is 6 bytes, 6 bits rather. How much memory can, and how many bytes is a page table entry? So a page table entry, remember, has to store the page frame, has to store whatever else is left in the address. So we said this is both the page frame number and the VPN. So we have roughly 10 bits here, plus some bits for valid bits and things like that. So we would need 2 bytes to store each PTE, because we need to store 10 bits for the page frame number, and then we have 6 bits for valid, reference, read, write, things like that. If we have a 64-byte page and we have 2 bytes for PTE, that leads to 32 per page times 64 bytes mapped by each PTE equals, 2 to the 5 times 2 to the 6 is 2 to the 11. So this is 2,048 bytes. So the key here was figuring out how many PTEs I fit on a page, which is just a page size divided by the size of a PTE, and then how many bytes does each PTE map, which is the page size. And I multiply those together, and I get the answer. So the next question was, assuming that each level of the page table is at most 1 page, how many levels of the page table are needed to translate all possible addresses? So the way we solve this is we have our 16-bit addresses, we have our 6-bit offset, and then we start saying, well, each level of the page table maps how many, has 1 page in it, how many bits of an address can 1 page map? Well, we have 32 PTEs on a page, that's 2 to the 5th, so that's 5 bits of address we can map. So our lower level will be 5 bits, and then fortunately we have 5 bits left over up here. And so we have to have 2 levels to map the whole thing. So we have 1 level up here with 32 entries, and each of these maps another level with 32 entries. And that's our page table. So it's almost exactly like the 32-bit case with 4 kilobyte pages. It's exactly the same problem, just all the numbers have been cut to half as long. Any questions on that part of the problem? Yes?
Can you go through the explanation again of why there's 2 bytes per page table?
Sure. So a PTE, inside a PTE, we have to think about what are the things that are stored in a PTE. The biggest thing is the page frame number. The page frame number is everything in an address, in a physical address that is not the offset. The problem said that physical addresses are 16 bits and they're 64-byte pages. So 64 bytes is 6 bits. That means the remaining bits are all the page frame number. So that means in the PTE, we need to have 10 bits to store the page frame number. Then we know we need at least 1 bit for the valid bit. And if we want to have a fancier PTE, we might need a reference bit, a modified bit, and then a read or read-write bit. So we need some extra bits. And so our 10 bits plus all of these roughly add up to 16 bits, which is 2 bytes. And so a PTE would be 2 bytes. Yes?
So your PTE doesn't necessarily have to use all 16 bits?
Correct. In most systems, the PTE actually has some empty space in it because it's better to round it up to a multiple of 8 bytes. And then you have bits in case in some future generation the company wants to add a new feature. For example, Intel used one of these empty bits to add an execute permission that they didn't used to have. And because they had some extra bits, they could add that without changing everything. Other questions? Okay, so the third problem was on interprocess communication, and it was asking about how would you construct these. The first one said you've got a large tree structure in memory, and then we have 4 processes that are searching for different things. How would we construct this? The answer I was looking for was shared memory. That it would be very natural to sort of put this large tree into one place in memory, then each of these processes can all access the same copy. This saves memory because we only have 1 copy of the tree. The processes in this question were all doing different things, so they didn't need to synchronize or coordinate because they're just searching, which means they're reading the tree and not modifying it, and they're searching for different things, so it doesn't matter if one finds something, the other one still has to keep working. So there's no need for messages or signaling here because they're all independently doing something on a shared data structure. The second problem was a variation of this that said there are 4 separate trees and you have 4 processes searching 4 trees, and you want the other, as soon as one process finds what it's looking for, the other 4 should stop. So this is an example of, suppose we take a problem and we split it into 4 chunks and we try to solve all 4 pieces in parallel on 4 processors. So here the thing to notice is we don't really need to communicate data because every process has its own private data structure it's working with. What we need to do is communicate sort of control that says one process is finished. And so this was a great map for signals because when one process found something, it could send a signal to the other processes saying, I'm done, you can stop looking. And so signals were the best answer here. The final question was, you're writing a search engine composed of 2 processes. The first process reads files in and creates a record, which is sort of an information about a word that it found in a file and where. And the second process takes those records and builds a hash table out of it. And so here I thought a good answer was message passing or producer-consumer, where one process sort of produces a bunch of data, maybe sends it over a pipe, or somehow communicates each of those records as a separate message to the process that builds the hash table. Because the communication is all going in one direction, it works out very well to just send the messages in one direction. Okay, any questions on that quiz? Okay, so the second thing we can talk about is the practice homework. If there are any questions on the practice homework, I can answer them. Yes.
Question 1. How is it clear how you got the valid bit?
Okay. So I actually printed this out and left it on the printer. So I'm just going to have to make up what it looked like. So what it said was something like your page size Say your page size is 4 kilobytes, the valid bit is the first bit, and then your page table looks like this. So it started off saying, here's your virtual page number, and there was a number that looked either like or something like this. So you were then asked and said, if you have a virtual address, calculate the physical address. So the first thing you do in reading this is figure out what is the page frame number. So we know the page size is 4 kilobytes. 4 kilobytes is what power of 2? It's 2 to the 12. 2 to the 12 is how many? 12 is how many hexadecimal numbers? Each hexadecimal digit is 4 bits. So 12 bits is 3 hexadecimal numbers. So I know that the offset is the lower 3 numbers in the address in hexadecimal. The good reason that people use hexadecimal for virtual memory problems. That means this is the offset. This is the virtual page number right here. I take my virtual page number. I look it up in the page table. And now there's 2 things I need to check. First I have to check is the valid bit set. The valid bit set is the first bit, which is this number right here. If this number is greater than 8, it means the high bit of this 32-bit number is 1. Because the highest bit of this because 8 this last digit here really is made up of 4 binary digits. There's a 1, 2, 4, and an 8's position. So if the high bit is set, it means that this number has an 8. The number has to be at least greater than 8. So if the entry in the VPN starts with in the page table starts with an 8, it means the valid bit is set. I then pull out the page frame number here, and I concatenate, and I get 37B333 as my physical address. So if I look at the second one, here my page frame number is 1. Here I look at my page table entry and I see the high bit is 0. This means the valid bit is not set. This means this is an invalid address. And that's all you have to do. Yes?
And on it, there were 2 other items at the top. Something like
the amount of physical memory. So the amount of physical memory and the amount of virtual memory. So these numbers were taken from a simulator written by Professor Apache Duso. So the amount of physical memory says what is the range of page frame numbers. If I had said the amount of physical memory was 8 pages, then it would mean that these numbers would be between 0 and 7 because I'd only have the page frame numbers from 0 to 7. By having more physical addresses, it says the range of the page frame number is much larger. But it doesn't affect at all how you answer the problem. The other question was, how big is the virtual address? The virtual address space. So the virtual address space affects how many entries are in the page table, because you have to have 1 entry in the page table for each page in your virtual address space. So by saying the virtual address space was pretty small, maybe 64 kilobytes, it meant that the page table in the example question was pretty small. If I had said that the virtual address space was 4 gigabytes, you would have had 1 million entries on that problem to look through. So that's how it affects it. The size of the address space is how big is the page table. The size of the physical memory is how big are your page frame numbers. Other questions? Yes?
Should we be double checking then that you're not telling us to access a frame that doesn't exist?
It wouldn't hurt, but I can tell you it won't happen, as far as I know. I mean, I'm trusting this other professor to write correct Python code. And you know, professors don't write a lot of code, so there could be bugs. Okay, so that was question 1. Were there questions on the other 2? I don't remember offhand exactly what they were.
Well, I think it was more in the wording. So I got confused about whether it was saying that, but never mind.
So there was one on copy on write, on sort of when is it beneficial. And there was another one looking at hardware TLBs versus software TLBs in the speedup. And I think people seem to be pretty clear on those, people who read the discussion forum. So if that is all the questions, then we might as well start this quiz and get it over with.